Hi, welcome back to Large-Scale Machine Learning. So we'll be continuing our discussion of gradient descent with large data sets. So in the previous video, we talked about how this particular experiment shows the effect of different learning algorithms, different learning rates and different optimization algorithms if we were to apply it to a stochastic gradient descent or gradient descent type problem. And you can see that actually for some algorithms like SGD, they can perform quite well, even though it's a relatively simple algorithm as compared with other more complex algorithms. But you should try with different locations within this contour plot of the different loss values, because depending on the trajectory, actually some of the algorithms may actually perform better. So in gradient descent, the idea is to basically minimize the error function, or what we call the loss function, which is if we use a very simple loss function such as the mean square error loss, right? So this is actually a squared loss function, basically the y, the actual value, minus the predicted value, and then we square it. So this is useful for regression type problems, and we can actually provide visuals for how the convergence occurs. And this actually gives us a deep insight into the choice of the optimization algorithm and also the parameters we want to use for these algorithms, whether it be it SGD or ADAM. So providing visuals for these type of algorithms and their way of convergence will provide a deep insight for the designer to select the best choice. Now let's say we don't really have an algorithm to learn weights. How will we approach this problem of learning? Random guesses, randomly putting the weights, right, could be one in order to solve the problem. But the gradient descent just basically means that we, instead of random guessing, which will take us forever to guess the right combination of weights, we try to use the gradient calculation to tell us the direction in which you need to adjust the weights. And this gradient descent algorithm has proven itself to be able to solve this problem in many cases. It may take longer for some problems, but it will still find the minimum point. But if the loss function is having a very complex curve, right? It's not a convex function. That means it doesn't have a simple minimum point. Then you might find that the SGD does not converge. But those will be the exception rather than the general case. So clearly we need the way to learn the weights. Okay, so this is basically describing the gradient descent functions, right? So the weight is the next new weight, WT plus 1 is actually the O weight minus a certain learning rate multiplied by a change or gradient function depends on the weight. And we can actually calculate this change, this delta W, by doing a differential of the loss function. So we basically move in the opposite direction of the gradient in multiple dimensions. So if we try to move downhill, basically. So if we want to move in the direction where the loss is becoming smaller, so we go opposite the gradient, because the gradient basically will be in the direction of increase in the loss function. So if you go uphill, you are basically following the direction of the gradient. So that will point towards where the loss function is higher. So if you want to minimize the loss, you should go in the opposite direction of the gradient, which is towards the lower value. So that's in essence is the intuition behind gradient descent optimization algorithms. But the learning rate is a parameter that can vary. It doesn't necessarily need to have to be a constant. So we can think about how we can adaptively change this. And the different learning algorithms, optimization algorithms may also implement not a single estimate of the gradient, but maybe a two-level estimate. That means we take one step, the next step, and then we take a further step away. So we have a more smoothed out estimate of the gradient rather than just taking one single point value. So if we have the contour plot, so the tree is basically a 3D representation, and you can plot it out this way. but it's very hard for people to visualize. So typically, in order for us to visualize the descent down the slope, right, we would use contour plot, which is a plot where the same value of the loss is plotted as a line, as a two-dimensional line. So all those along the same contour is the same loss function. So this is like rings around the hill, right? So all those, and this is actually quite is what I call a topo map, right? A topology map. So it will actually give you uh, the same slope level or the same height level wherever the ring is the same. So all these are the higher values. Here the color scheme is slightly different. So the lower values, okay, are actually in blue. The valleys are in blue, and the top of the hill are actually in the more brownish shade. So this thing actually rolls down the hill towards into the valley. So if you have a starting point here, it calculates that the gradient actually is actually going downhill in this direction. Negative gradient is actually in this direction, and you can see that it will accelerate where the contour lines are closer together because it is actually steeper. So if you look at the 3D plot, where the contour lines are closer together, it means that actually the slope is actually steeper. And therefore, whatever gradient descent algorithm you are using would accelerate because the gradient computation will give you a larger value. So you can see that if we represent it with arrows, the arrows are closer together, whereas speeding down the hill, once it reaches the bottom, the contour values then basically flatten out because it's the bottom of the valley, and then it will actually approach the minimum point in a much slower manner because there are many close minimum points in this particular value. So now if you have the overall plot, you can actually decide that, hey, actually I do not need to find the absolute minimum in this entire valley. I can just pick the first few minimum point, because even though I find a solution here and it's not actually the absolute lowest point, but it's actually pretty close to the lowest possible within this entire space. So it's no point we actually run the algorithm for a very long period of time and we don't actually get very much improvement in the performance in terms of finding the lowest loss value anyway. So you can see here we use 2D contour maps for the error surface to give you the equivalent power, and then if we analyze this, the steep slope, the fast changing will be here, and we can see the arrows where it's actually moving quickly, and then actually once it reaches the bottom it actually slows down. So in this GIF diagram actually shows the visualization of the different algorithms, SGD with momentum. This is a Nesterov accelerated gradient function where we actually have a two-step estimate, right? Instead of just estimate with one single delta, it actually takes the 2 steps ahead and uses that to actually estimate the gradient. So it's actually faster, so it gives you a more accurate estimate of the gradient. Then we have the adaptive gradient, ADAM, and adaptive with delta and RMS prop. So you can see if we have a very complex kind of a loss function, so you can see that the high values and the low values, they are not gradual anymore. You can actually change very rapidly, where there are steep slopes in some places like over here, and then more gradual slopes over here, and then you have low points and high points being mixed up. So you can see that some algorithms that like the momentum one, right? When it starts from this point, because it's very steep, it moves very quickly, but it overshoots this low point because the gradients here are actually changing very slowly. So it overshoots, went over to the other side, and it hits the wall where it's actually having a very steep gradient, bounces around a bit, and then finally comes back. This is the behavior of the momentum-based one, where it's based on the change in the velocity rather than just it's based on the previous velocity rather than just the next gradient estimate. So it has some memory of the past step size that it changed. So because of that, it has this notion of momentum. It will continue to move in the same direction. So once it speeds up very quickly because of the initial high slope here, it sort of overshoots, went to the other side, and then bounces back. Now, if you look at the brown one, the SGD, it actually sort of yeah, it actually doesn't went to the other side. It actually comes back. Oh, but you can see that as compared with the other algorithms, the SGD is moving smoothly, but slowly as compared with the other. The other two already reached the destination, the endpoint before the SGD even reaches close to it. This is SGD one. It's quite smooth, but it's very slow. Right, you can see that it's actually moving very slowly because the rest of them have adaptive learning rate, so they can actually move much faster. So the one that I mentioned just now, the purple one, the NAG, right? You can see this one because it really accelerates very fast. It also, just like the momentum, overshoots, but then it is able to return back to the minimum point a lot faster than the pure momentum based one. This behavior is partly because of this rather weird configuration of loss functions where you have a region where it's basically flat next to a very high slope area, and yeah, and we purposely started the thing at the high slope area so it will actually gather speed and then overshoot. If you had started somewhere else, for example here, you wouldn't have the same behavior. Okay, so it's so that's why when we actually train this kind of gradient descent algorithms, we normally have a randomized starting point so that we don't end up being biased against certain algorithms just because of the way we set the starting point. So it's important to have some amount of randomization so that we sort of even out the playing field so that all the algorithms, if they're really that superior, they will naturally be able to show that they can reach the lowest point faster. So certain algorithms like those with momentum and also the NAG, they are not able to handle certain special conditions. Like for example, there's a very narrow valley where the minimum point is actually within here, and then it is very narrow because the sides are very steep, and we start at actually at a point that's actually high ground. Because of the momentum mechanism, we find that you will actually bounce around the valley walls a lot. Okay, because these are the direction of maximum gradient, so it actually basically bounces around the edges a lot before it finally settles into the lowest area, the lowest minimum point. So this is because of the behavior of momentum based one. Now for stochastic gradient descent, it will also bounce around, but maybe not as much as the momentum based gradient descent. Now why do you have this kind of valleys, long narrow valleys as compared with steep sides? One of the possibilities is basically due to feature scaling. So if you have some values that are very large, okay, they change very rapidly, and then another set of values where it actually represents this dimension, where the actually a very small value, so it doesn't change very much. So if you don't scale the values in this kind of gradient descent algorithm, it's very sensitive to feature scaling. So you will end up generating this kind of narrow valleys because you don't have a same range of values for each of the features, and the algorithm is not able to overcome it, right? So the algorithm can be optimized, but because of the fact that the features are not being scaled correctly, therefore it will end up bouncing around a lot over the side walls, as you can observe here. You can improve this by changing the learning rate or the momentum, or you can also improve this by just making the surface not so steep as in certain directions only, okay, by doing feature scaling. So let's take a look at another optimization algorithm for the gradient descent, and that's the Nesterov accelerated gradient. This is the one that takes like a two-step ahead kind of estimate. You can see that it also bounces around, but it does converge a lot faster. So the red one is the momentum-based one, and the blue one is the Nesterov or NAG. And you can see that NAG actually reaches the minimum point a lot faster because it doesn't bounce around as much. So the energy is able to actually converge better than the momentum method, and moving it a bit, the gradient after that point makes it basically is able to get a better estimate of the gradient as compared with the momentum based only. So all the U-turns are made within the boundary of the momentum-based method, but by energy, hence the oscillations are reduced, and this correction in cost is much faster. So you can combine the two. You can have momentum with energy so that it can actually estimate the gradient better and then converge faster to the lowest point. And of course, what I mentioned just now, scale the values so that you don't end up generating these kind of values in the loss function. Okay. So with a stochastic gradient descent, which is a stochastic method, we are estimating the gradient rather than calculating or averaging the gradient over a large input set, okay, a large training set of data. So we take one example out of the whole entire training set and use that as the approximation for the gradient at each iteration. Now this algorithm will make update at every single iteration with one random sample from the entire dataset. Now, if you take sufficient number of samples, obviously you will still cover the entire epoch, right? All the data within the neural network. So it will take a couple of million updates for it to actually cover one epoch. Again, this is still actually ultimately a satisfactory solution because the approximation doesn't guarantee each will be the most optimal step, but it will generally move in the correct direction. It's almost like tossing a coin. And you can observe that it results in this jittery sort of behavior. It does move towards the lowest point, but it doesn't move in a smooth smooth movement because each iteration is likely to be slightly off target, right? Although it's moving generally in the right direction, but slightly off target. So at the next iteration, it corrects itself and then it moves in a slightly different direction. So hence you get this like small zigzags around as it moves towards the lowest point. So that it takes many oscillations with greedy decision making, and each point, each data point, basically gradually nudges right the gradient, the the algorithm towards the lowest point. Okay? Each point it just pushes it a little bit further, but it may not push it in exactly the same direction. Therefore, you see these jaggy lines as it rolls downhill. So it's almost like as though every data point is just competing with each other to try to push it or nudge it a little bit further along. Now, if you actually use the stochastic gradient descent, not just based on one random sample, but based on a group of samples, or what we call mini batch gradient descent, then the estimate becomes slightly better. It is not as extreme as taking the entire dataset as the batch, nor is it as rough as just taking one sample out of the entire dataset. So we take groups of data randomly picked, and this averaging effect, right, basically means that my gradient estimate is more accurate, and therefore you can still see there's some amount of jagginess as it rolls downhill, but it is definitely less pronounced than the pure stochastic gradient descent, where we just take one single sample per iteration and we use that as an estimate. So now we take the average of several different guesses, right, and we calculate based on these several different randomly sampled data, what is the gradient, and then it basically gives you a more accurate estimate of the gradient, and therefore the descent is more smooth. This is basically called the mini batch gradient descent. It's a variation of SGD. You can think of it as SGD with more than just one random sample. Okay, it's SGD with several different random samples combined together to give you the average. But it's definitely much more efficient than the batch computation of the gradient, which takes the entire data set. So but with very large data set, it's not practical to use the entire data set every iteration you want to make in updating the weights. So in scikit-learn, SGD is actually an optimization method for unconstrained optimization problems, and basically we can actually implement different machine learning algorithms depending on the loss function. So this was mentioned before. If you use the hinge loss, we can basically implement a support vector classification. If we use a perceptron, we can use the max loss function. If you use a Huber loss, you will get a slightly different function. And if you use the log loss, we get logistic regression. If you use the least square, we get linear regression. If you use Huber, it's slightly less sensitive to outliers than least squares. Where it basically implements the same kind of linear regression, but with less loss, less sensitive to outliers. And lastly, we can have a soft margin. Right, it's basically support vector machine with some regularization factor placed in. So this gives it the flexibility. By modifying the loss function, we can actually implement different algorithms with incremental learning using SGD. So here's a quick quiz of what can affect a gradient descent algorithm. Is it A, momentum, B, learning rate, C, the NAG, D, Adam, E, all of the above, or F, none of this above? So think about the answer and pause a while before you move on to the next part of the video. And with that, we come to the end of this set of slides. So thank you for your attention.